Okay, so Namaste, Sat Sri Akal, good morning, Adab to all of you. Thank you for coming uh, to class. I'm very happy that how many people? That 19 people come to class on a mostly regular basis. Not 19 people, sorry, 2 of those people are me only. So I guess 17 people out of class strength of 30. So I think that is not bad. That is okay. Okay. Yeah. So this is my daughter actually. She's cute, na?
Yes, sir.
She's very
So cute,
Yes,
sir.
sir. So cute.
ऐसे देखिए, we do this, right? What does it mean? It is actually not. It is not a very scientific thing, but when it comes to Shubham ji हंस रहे हैं.
अरे
So, huh? What Shubham?
सर नजर नहीं लगेगी.
क्या? हाँ, नजर कैसे लग सकती है बताइए. जाको राखे चाहिए नजर लग रहा है ना कोई. ठीक है तो so yesterday in up till Monday's class, see, I had gone over this very carefully with all of you. So I hope that all of you who attend my class regularly, I'm very happy that you attend the class regularly, but it is equally important that you not just attend, but that you work through all the lecture notes, that you do some of the practice problems at the end of the chapter. I haven't like given you any exercise problems as such, but maybe I will do that. But you can also look through the problems and try to attempt some on your own. So today we will look at a couple of examples of Ehrenfest theorem in action. And the other thing that I want to start talking about is so we have talked about 1D harmonic oscillator and 1D particle. And so now what happens is, of course, in life, in nature, we have more than one dimension. We have 4 dimensions, right? We have, well, actually 3 spatial dimensions and 1 time dimension. So in the most general case, we would consider a particle to be moving as moving in 3 plus 1 dimensions. So we have talked about a harmonic oscillator or a particle moving so far only in 1 plus 1 dimension, right? 1 space and 1 time dimension. So we'll talk about the 3-dimensional infinite potential well, and then other such questions. So what we have found so far, by the way, is that so this is an important aspect, that if you have anything that commutes with a Hamiltonian, then that quantity is a conserved quantity. It's a constant of motion, right? So this is true for both classical and quantum mechanics, right? But the difference is that in the classical case, so for classical case, we have, instead of, so this is the thing that we have Poisson brackets. So this is one thing that I don't know how how much you have learned in your undergraduate courses, because not all undergraduate courses properly teach classical mechanics, and that you have this notion of Poisson brackets, and in quantum mechanics, so this is in classical mechanics, and in quantum mechanics, these Poisson brackets are replaced by commutators, right? Commutators of operators. And so it is important to keep in mind that there is a parallel between everything that happens in classical mechanics and quantum mechanics, right? So for instance, in quantum mechanics, we have the equation for the time evolution of any observable, right? So if you look at this equation, right, this is the fundamental equation which gives you the relationship between an operator at an earlier time and an operator at a later time in terms of this guy. What is this? What is this exponential, this thing? This is what they call the time evolution operator, right? So if you write down this relationship, and it can be written in this way, right? UT O or UT minus T naught O at T naught, and then UT minus T naught, right? So this is a similarity transformation, right? If you remember that if you have any operator, for any operator O, you have O prime is equal to U O prime U inverse, right? This is called a similarity transformation. Straight line. So if you take now we can take the time derivative of both sides of this expression, right? So if we take the time derivative, we get this O right, just by using Leibniz rule. Can you all see this, or should I make it a little bigger? I think maybe I'll zoom in a little bit. If you want, you can hide. Well, I don't know if it's possible to hide the speakers gallery. Then that makes the screen a little bit bigger. Anyways, so now these two terms, the first term and the third term, together what they do is they give you the commutator between, when you take the time derivative of this unitary operator, right? What happens? You get 1 power of the Hamiltonian comes down from the exponential, right? So when you take this thing, so don't confuse this u with this u. Okay, I'm using the same symbol, but one is an exponential, the other is. So when you take the time derivative of this operator, what will happen is you'll get 1 copy of I over h bar and 1 copy of h that will come outside. And then in one term you will have h bar comma O, and the other term you will have O comma h bar, right? And so those two together will combine. So you'll get minus I over h bar h comma O, that's plus I over, so you'll get minus I over h bar commutator of h and O. And then this last term, this term can be written as d do by dt. So in the event that O has some explicit time dependence, right? In that event, this middle term is non-zero. So what we have in quantum mechanics is this Heisenberg equation of motion, right? Which tells us how operators evolve in time. And I hope I've gotten my sign right in the evolution equation. Okay. And the thing is that in classical mechanics, we have exactly the same equation of motion for any function on the phase space, right? So in classical mechanics, we say that we have functions on the phase space where, so f is a function on the phase space. So what is the symbol for phase space? Call it gamma to r, right? So PQ are the phase space coordinates, and f is a function from gamma. What is gamma? Gamma is the space of these momentum and position coordinates, right? And what is this quantity? This quantity is the Hamiltonian, the Poisson bracket of the Hamiltonian with the function plus the partial derivative of the function with respect to time. So the thing is that, and again, I might be making a mistake with my signs. It's important to get that right. Okay. Where is what's his name? Chinmay. Chinmay is not in class today. I generally rely on him to correct such mistakes on my part. Okay. Okay, never mind. This is, yeah, so you can check the sign over here whether this sign is correct or not. Okay, but this is basically what it looks like. So let me make just check one thing. You get minus I h bar. And that will be, I think, yeah, this is, I believe this is the right sign. Yeah, so there might be a minus sign over here. See, it doesn't really matter whether it, I mean, it does make a difference whether you put I or minus I, but again, once you pick a sign, you have to stick with that sign. So the correspondence between classical and quantum mechanics is roughly the statement so that you go from operators, you go from functions on the phase space to operators on the state space of quantum mechanics, the Hilbert space. And the functions on the phase space are translated into Poisson brackets, the commutators of the corresponding operators. And there is some sign here, plus or minus, because you have an I. The sign, again, is a matter of convention, but we have to be careful. We can't arbitrarily change the convention in the middle of, so that is one thing we do have to be careful about.
Sir, what is the symbol that in the second last line?
Which symbol? Omega.
Sir, ओमेगा है वो अच्छा सर वो फंक्शन ऑफ पी एंड क्यू के बाद जो लिखा हुआ है
हाँ that is gamma sorry, capital gamma. That is
Okay,
capital
sir.
gamma, right? You have small gamma and then there is capital gamma also,
Okay, sir.
right? Small gamma is this and capital gamma is this, right? This is a Greek alphabet, na? So minus, yeah, I think the sign is right, but h bar should be in the denominator. That was my mistake. H bar should be in the denominator. Okay. Now, so what are these Poisson brackets? If in case you may or may not remember, so let me remind you what these Poisson brackets are. So you have two functions on face, any two functions, or you can have an infinite number of functions on the phase space, and this is given by this relationship. So you might be learning all of these things right now in your classical mechanics course, and so yeah, so let me again correct my mistake. This is goes to minus I over h bar, not I times h bar minus I. Right. So the fact that classical mechanics and quantum mechanics are so similar to each other, right? You can look at this structure, and there is, I mean, it seems like they look the same, but they are not the same, right? Because in classical mechanics you have this phase space, right? And you have functions on the phase space. So, for example, if you write down a Hamiltonian for a free particle, p square by 2m plus 1 half kx square, or harmonic oscillator. What is this? This is a function, right? And I'll put, instead of x, I will use q. This is a function of these two variables, p and q, right? But in the quantum case, when I write down this equivalent expression in terms of the p and q operators, in that case, I cannot write this as a function of, I mean, it is an operator. It is a function of operators of p and q. Okay, so I can write it like this, let's say. But this is not equivalent to a function of, let's say, something like this, of the position and momentum eigenvalues. Why? Because here in the quantum case, what happens is that if you look at the commutator of q and p, right, the commutator of q and p is not zero. This is very important, right? In the classical case, the commutator of q and p is zero. And now so now we can use this analogy to we can use this equation of motion, this one, to write down the time evolution of various kinds of operators and states. So as an example, let's say we want to know what is the time evolution of the position operator, right? So in the classical case, what would you say? In the classical case, you would say, I'm calculating the time derivative of dx by dt. In the quantum case, you would say, what is the time derivative of the operator x. And then from this operator x, you would make some measurement. And when you make a measurement, that measurement would give you an expectation value of dx by dt, the operator dx by dt, right? So this would be the expectation value of the velocity. In classical mechanics, of course, you don't need that. In classical mechanics, you just have v is just a number, dx by dt. You don't have to make any measurements, right? And now, if you look at this Hamiltonian, and you insert it into this expression, you have this expression over here, and you ask what is the this Poisson bracket between, let's say, this Hamiltonian and our function f, right? A function f on the phase space. F can be, it can also be, so again, I'm using x. I should probably use q because I don't want to, be inconsistent. I'm using x somewhere, q somewhere. So f is some function of p and q, right? So one such function is just q. Q is also a function of p and q, right? So for example, if I have this x and f of x, then f of x can also equal to x, right? That's also a function of x. It's a sort of a trivial kind of function. So I can insert this into my Poisson bracket for the Poisson bracket. And again, I got one more sign here wrong. This should be f comma h, or I can write h comma f and then put a minus sign here. So I can ask what is dx by dt. So dx by dt would be given by negative Poisson, this Poisson bracket of the Hamiltonian, this Poisson bracket with x plus partial of dx by dt. And what is this? So as an example, let's say we consider h to be our something like this, right? Now you see this Hamiltonian has a kinetic energy term which depends on the momentum and potential, but this potential is independent of momentum. This is very important, right? So when you take this Poisson bracket of h with x, what will you get? You will get the Poisson bracket of the first term with x plus the Poisson bracket of the potential with x, right? So the Poisson bracket is a linear functional, this thing. So if I have if I take the sum of two functions, let's say f comma g plus h, then this is equal to like this, right? So the Poisson bracket and the commutator, they are both linear objects, okay? The same thing applies for commutators also, right? Now, what is this quantity? What is the commutator of the potential of this thing? Well, if you work it out, this will be 0. Okay, basically, any function of x will commute with x. In general, if I have two functions which are only functions of x, they will commute, or the Poisson brackets will be 0. Again, I'm sorry, I'm using x instead of q, force of habit, but please keep in mind that x equals to q. Okay. And similarly, if you have any two functions which are functions only of momentum, then those two will also give you 0. You can check that explicitly. I mean, it's not difficult, right? So you can use the definition of this f comma g. So if you only have one dimension, then in this expression for the Poisson bracket, there is no sum. Sum is not there, right? There's only one index I. So it becomes df by dq, dg by dp, right? And you can see that if g does not depend on p, for example, then this term will be 0. And if f does not depend on p, then this term will be 0. So if neither g nor f have any dependence on p, they only depend on x, what will happen? This whole thing will be 0. The same thing applies if both of them only depend on p but not on x. Okay, you can see that explicitly, right? It's very simple to see that. So this Poisson bracket b of x with x is 0, right? And the non-zero Poisson bracket will be this p square by 2m comma x. So what is this guy? Well, the first term is this f. So again, going back here, you get df by dq or df by dx. So d time d of p square by 2m by dx. And then the second derivative or the second expression is this dx by dp, right? Then minus the same thing, but now you have a derivative with respect to p, right? So what does this give us? This gives us, the first term will give us 0, right? Because these derivatives are 0. And the second term, this will be equal to 1, and this term will just give us minus p by m, right? So we find that this is equal to p square by 2m comma x is minus p by m. And what about the dx by dt part? Well, this term is obviously 0, right? Because x is not a function of t, right? Now, so if you look at this, if you insert this into the time evolution equation, what do you find? Dx by dt is equal to minus h comma x, and then partial derivative, but that is 0. Okay, so I'm sorry, I should not put this here. And this is 0. And what is this commutator? This commutator is p by m, right? So finally, what do we have? We have this relationship, v is equal to p by m. But this is expected, right? We know this already in classical mechanics. The velocity of a particle is just the momentum, or the momentum is the mass times velocity. No surprise here. Okay. But now we can ask the same question for the quantum case. Okay. So for the quantum case, we can ask what is the, so this is the classical example. And then for the quantum example, we can ask what is the time evolution of the position operator. And then we have the Heisenberg equation of motion, which is minus I over h bar, commutator of h with respect to x, plus this if there is any explicit time dependence of x on t. Okay. This term is 0. This term will generally be 0 unless there is an explicit dependence. An explicit dependence can arise, for instance, if you go from one frame of reference, if you happen to be in a frame of reference that is, let's say, rotating with respect to another frame of reference, right? Then you will get such a term. Okay? But if you are not in such a non-inertial term, in non-inertial frame of reference, you will not get such a term generally. So now what is this commutator of h and x? Again, this is a commutator of p square by 2m plus v of x with x. And this is commutator p square by 2m with x and commutator of v of x with x. Once again, this is 0, right? Why? Because we know that x commutes with x. Right?
Sir, I think there should be a commutator of x comma h.
Sorry?
So I think there should be a commutator of minus I upon h cross is in the commutator. I think that there should be x comma h.
So it doesn't, see, I put a minus sign here, na?
Yes, sir, but with the minus sign, I think.
With the minus sign,
Yes, sir.
h comes on the left. This becomes commutator of h comma x. If I don't put a minus sign, then I will write down commutator of x comma h. So, sorry, so, wait a minute. I think you're right. Again, my mistake. You're right. This should be minus. Yeah, it should be x comma h. Thank you for pointing that out. So this is. So now what is this commutator? Well, the potential with this thing is 0. Okay, so this is 0, and we need this commutator. So we need to ask what is the commutator of p square, operator p square with x. Now there is a operator identity. I'm going to write it down, and I'm not going to prove it. I'll leave that proof for you for the 6th homework set. Okay. So homework number 6. I think I've not given you any homework 6 problems, right? Have I given you anything? Yeah, I've given you some problems previously. Homework 6, problem number 3, I think. Prove that x comma p to the nth power is equal to I times n times h bar times p to the power n minus 1. So this is very similar to the question that I had given you in the quiz for A and A dagger. And then using this, also prove that if you have x and some function of p, then this is equal to IH bar df by dp. And similarly, p of some function with only of g will give you minus IH bar dg by d. So to prove this, what you do is you expand these, you use a Taylor expansion of these operators, of these functions. So you can write this, the first term as just the identity operator, then the second term is p, then p square by 2m, and so on. Right? So you write down a Taylor series expansion of this, and then for each term you apply this expression, and you will see that, on the right side you will get this expression. by taking the derivative of this operator. So how do you take the derivative of this series? Well, this is just 0 p by 2m, and so on. Okay. So yeah, sorry, this is the Taylor series expansion. I have to be careful. So the Taylor series expansion will be f of 0 times p hat plus p square by 2 factorial. So okay, yeah, let me be careful. This is equal to f of 0 plus p hat times f prime 0 plus p square by 2 factorial f double prime 0. F of 0 just means that if I put 0 as an argument, okay, what is the result? And something got overwritten. I think this is dg by dx. Okay. So when you calculate this p square comma x, again, this is not difficult, right? We can just write down, okay, and sorry, this should be a commutator sign, not a personal bracket sign. So you get p times px plus px times p, right? And this is equal to minus IH bar, this is equal to minus IH bar. So you get minus 2 IH bar times p hat. Right? So I can commutate personal bracket, commutator. So once I insert all of this into this expression, on the right side, what will I get? On the right side, I will find that dx, the operator x by dt is equal to, so when you look at the factor of I over h bar, and you have a factor of 1 by 2m, so the 2 and the h bar will cancel out, and the signs of minus will cancel out, and you will be left with this expression. So now if you look at this expression looks exactly the same as a classical expression, right? What is the classical expression? The classical expression is this guy, right? That dx by dt is equal to p by m. And in the quantum case, we are getting the same relationship, right? So whenever you have a potential which does not depend on momentum, right? And this is the case in many systems, then you get such a relationship. Okay. So this we can think of as, so we have not, this is the one step on the proof of this thing, Ehrenfest theorem. Now we can do exactly the same thing by calculating the time derivative of the momentum operator. So the time derivative of the momentum operator, when we calculate it, what will we get? Time derivative of momentum operator is same thing here, minus I over h bar, commutator of p comma Hamiltonian plus dp by dt. What will this give us? P comma h bar. Again, h bar is p square by 2m plus v of x. Now the commutator of P and P square is 0, right? So this will give me V comma. Now this is the commutator of P with a function of X. So I can use this result that I mentioned earlier. And this result, so this tells me that this is going to be equal to minus IH bar dV by dx hat, not P hat, dx. When I insert this back into my expression, I will see that this is equal to minus dV by dx hat. Plus dx hat, right? So now if you can take the expectation value of both sides, and if you take the expectation value, what do you get? You get d times dt is equal to minus expectation value dv dx plus d times expectation value. Okay, and what is this? This is Ehrenfest theorem. Now you might ask, why am I taking expectation values? I mean, I can just say that Ehrenfest theorem, that just this expression is Ehrenfest theorem, the operator
X
version.
cap na sir, dx x cap by dt.
कहाँ पे ये?
No sir, second term.
Okay, thanks. No, so this should be P, no? This should be P. Yeah. This should. So yeah, this is Ehrenfest theorem. Okay. So for this problem number, for the next homework, right? What you should do is homework number 6, problem number 4. So this is Ehrenfest. Now, the one thing to remember is that the expectation value depends on the state. So it's up to us which state we take the expectation value in, right? We can take the expectation value in any state, right? So using psi is equal to for the harmonic oscillator, first is the number operator eigenstate, and then is the coherent state alpha. For these two states, evaluate dp by dt, right? So how will you do this? You will calculate the left hand side. Now this expression is going to be 0. The momentum operator doesn't have any explicit time dependence. And what is this derivative of the potential? So the potential is 1/2 kx squared. When you take the derivative, you just get kx. So you just have to calculate expectation value of minus kx, right? So it's actually very simple. Okay. So I'll leave that. So I think we are done with Ehrenfest theorem for the time being. If we need to, we'll come back to it later. So Ehrenfest theorem, Heisenberg picture, Schrodinger picture, time evolution. For the time being, we are done with these things. We will come back to the time evolution when we look at we will look at some problems involving time evolutions of quantum states. Now, the next topic that I wanted to talk about was this thing, 3D infinite potential well. Do you have a class right now? Is there a class?
Yes,
right after
sir.
this? Okay. All right. So I will leave this for next week. And please remember, your mid-sem exam will be on the 7th of December. In case you have a conflict on that day, you have to let me know well in advance, okay? So that I can make necessary arrangements. Okay. And now, see, again, if you did cover Hamiltonian and Lagrangian mechanics in your undergraduate courses, you should go back and review that, okay? Because you might have forgotten all of these Poisson brackets and all that. What is Poisson bracket? So what does this Poisson bracket mean physically? Right? What does it do? Poisson bracket, what it does is it generates what is known as a canonical transformation, right? So canonical transformation is some change of coordinates. P goes to P plus delta P and X goes to X plus delta X, right? And the thing is that when you talk about this time evolution, when you look at this momentum as a function of time, your phase space doesn't change, right? Your phase space remains the same. And 1 second, my computer battery is low. All right. So your phase space, so you can think of this time evolution as a change of coordinates on your phase space, right? Whenever you have, for instance, one second, I'll answer that question. So whenever you have, for instance, you say that X is a function of time, you can also, instead of saying that X is changing, you can shift your coordinate axis, right? You can treat that function of time as something which, instead of the particle moving, you can change your coordinate axis. So same way, any time evolution in the phase space can be treated as a coordinate transformation, an infinitesimal coordinate transformation. And what these Poisson brackets they do is they generate these coordinate transformations. The Hamiltonian is the one which generates, which is what we identify with time evolution, right? So you can have an infinite number of functions on the phase space, right? You can have any function which is a combination of P and Q on the phase space, right? You could have exponent P times sine Q. You can have all sorts of crazy things. So technically one can use any function on the phase space as a Hamiltonian, right? So, but we use certain particular choices because they correspond to what we experimentally identify with the energy of a system. And in the quantum case, the commutator can again be thought of as a sort of a generator of certain something known as a gauge transformation, but that will make things too complicated, so I won't mention that. Then somebody is asking a question: if system is not known to be classical or quantum, then using Ehrenfest theorem, we can't know whether the system is quantum or classical, right? So this is a good question. This is a really good question. Yash is asking this question. So, and that's correct, but only if you restrict yourself to expectation values of the operator, right? But the thing is that, see, one has expectation values of p, right? But there are also expectation values of p square and p cubed. These are also all operators, right? And expectation value of p to the n, right? So what will happen is that what the Ehrenfest theorem is saying, that it only applies to the expectation value of these terms which are linear, right? So if I look at some function of p, if I ask, does Ehrenfest theorem apply to if I have dp by dt, then what about any arbitrary function of p? What is this? Right now I can write down, say, some arbitrary function of p again in some kind of a Taylor series like this. Okay. And what will you find? You will find that d of f by dt, right, will give you, so the first term will just give you 0, right? The second term, when you look at this expectation value, the second term will give you this f prime 0 times expectation value of dp by dt. So Ehrenfest theorem only applies to this guy, right? But if you want to calculate the full time evolution of the function, you also need these higher order functions, right? These higher order derivatives and the higher order expectation values, right? And so the thing is that these higher order expectation values will allow you to determine whether the system is classical or quantum, right? So in general, these quantities will not be 0 for, I mean, they will be different for the classical case and the quantum case. So if I calculate the expectation value of p square, that in general, that will not be equal to p square, right? And similarly, Pn, expectation value of p operator n, will not be equal to the momentum. So the better way to write it is like this. This will not be equal to expectation value of p to the power n. Right? In one case, you have n is inside the expectation value. In the other case, you have n outside. And so this will allow you to distinguish between the quantum system and the classical system. So that's an excellent question. Okay. Any other questions? Any other questions? Okay, I'll stop the